Hello, everyone. And so thank you for the introduction. And thank you for inviting me to talk about the imaging technique called line field confocal optical coherence tomography, LC-OCT. So LC-OCT is a technique invented in my lab at the Institute of Optics, and which is industrialized by the company DAMAE Medical. And this imaging technique is used in dermatology for the non-invasive diagnosis and the therapeutic control of skin lesions, including skin cancers. LC-OCT is also used in cosmetology for the quantification of skin. So I'll start by talking a little bit about dermatology, and then I'll move on to cosmetology. Skin cancer is the most common cancer in humans. The incidence of skin cancer has increased in recent decades, especially in the US, in Western Europe, and in Australia. There are two main kinds of skin cancers: carcinomas. They are the most common type of skin cancers. Carcinomas develop from keratinocytes, and melanoma. Melanoma is less frequent, but more dangerous. Melanoma develops from melanocytes. There are several precancerous skin lesions: actinic keratosis, lentigo maligna, Bowen's disease. So in dermatology, the standard diagnostic procedure begins with a visual examination of the surface of the lesion. If the lesion is suspicious, a biopsy is taken and the tissue is processed for histological analysis. This procedure has some disadvantages. It's expensive because so many biopsies are performed. It's invasive, resulting in pain and scarring. The procedure takes a long time before diagnosis can be made, about 2 weeks. And it's not very precise. About 60% of biopsies were in fact unnecessary, and about 20% of all skin cancers, including 1 in 3 melanomas, are not detected at an early stage. To improve the diagnostic process in dermatology, it's of interest to have a non-invasive imaging technique capable of providing images with a cellular resolution, a resolution similar to the resolution of histology. The technique should provide vertical sections like histological images, and possibly also horizontal sections, and also 3D images if possible. The technique must be applicable in vivo, and it should be a handheld device for convenient use. Several techniques have been developed for imaging in dermatology. The most common high-resolution techniques are reflectance confocal microscopy, RCM, optical coherence tomography, OCT, and more recently, line field confocal optical coherence tomography, LC-OCT. LC-OCT is a combination of confocal microscopy and OCT. So as a combination of both techniques, LC-OCT improves the penetration of confocal microscopy and improves the resolution of OCT. Here is an image of skin obtained by OCT, conventional OCT. And here is an image obtained by LC-OCT. As you can see, LC-OCT improves the resolution of OCT, but the field of view is reduced. Here, 1.2 millimeter laterally and 0.4 millimeter in depth. With a resolution of 1 micrometer in all directions, the LC-OCT images are comparable to histological images. High resolution is the major advantage of this technique of LC-OCT. I will now explain the principle of LC-OCT briefly. LC-OCT performs a kind of ultrasound imaging, but with light instead of ultrasound. Light penetrates the skin and is reflected by biological structures. By detecting optical echoes, we can reconstruct an image of the reflecting biological structures. So this is the idea in LC-OCT. In ultrasound imaging, the tissue structures are localized by measuring the travel time of ultrasound. This measurement is not possible with light, as light propagates much too fast, around 100,000 times faster than sound in tissues. So to get around this problem, an indirect measurement is made using interferometry. So let's talk about interferometry a little bit. Here is a schematic diagram of a microscope interferometer. A beam of broadband light is sent into the interferometer, which divides the beam into two beams. The two beams are reflected by mirrors, and they are then recombined at the interferometer output where they can interfere. As light has a broad spectrum, a low coherence, interference occurs if the two beams have traveled approximately the same distance. So if we vary the length of one of the interferometer's arms, we observe only a few interference fringes, and the width of the interferogram corresponds to the coherence length of light, which is inversely proportional to the spectral width of light, delta lambda. Now let's replace one of the interferometer's mirror with an object made up of several partially reflecting interfaces located at different depths. When we vary the length of the reference arm of the interferometer, we observe several peaks. Here, 3 peaks, because we had 3 interfaces. So the envelope of the fringes gives the 3 peaks, and the positions of these peaks correspond to the positions of the reflecting interfaces. So this is how we can detect optical echoes from in-depth structures using interferometry with broadband light. This is how optical echoes are measured in optical coherence tomography, OCT. So this is a general principle of OCT. As you can see here, the axial resolution in OCT, the ability to resolve structures at different depths, is given by the coherence length of light. This is a particularity of OCT. So this interferometric detection is the basis of line field confocal optical coherence tomography, LC-OCT. As you can see here on this schematic diagram, LC-OCT is based on a microscope interferometer with a microscope objective in each arm. So it's an interferometric microscope. The sample is illuminated by a line of broadband light. The interferometric signal is detected by a line scan camera. So LC-OCT can be considered as a combination of OCT and confocal line scanning microscopy. The line illumination and the line detection, combined with the use of a microscope objective, provides a confocal gate. This confocal gate prevents the detection of the light scattered from the sample that does not contribute to the interferometric signal. So with this technique, with LC-OCT, imaging at high resolution, 1 micron, in highly scattering tissues such as skin can be achieved to a depth of about 0.5 millimeters. By scanning the line of light vertically using a piezoelectric stage, a vertical cross-section image can be obtained in real time at 8 frames per second. And by scanning the line of light horizontally now, using a galvo mirror, a horizontal section is obtained in real time at 8 frames per second. And finally, a 3-dimensional image, a 3D image, can be obtained from a stack of horizontal sections in a few tens of seconds. So here, this is an illustration of the performance of LC-OCT for skin imaging. Here it was skin on a finger. So here in a vertical section, 3 main layers can be distinguished: the stratum corneum, the epidermis, the dermis, separated by the dermal-epidermal junction. The nuclei are also visible. All these dark spots in the epidermis are the nuclei of the keratinocytes. Blood vessels are also visible. And here on your right, we have 3 horizontal sections occurred at different depths in the stratum corneum, in the layer of the keratinocytes, and in the dermis, where collagen fibers can be observed. I will now present the development of the LC-OCT technique carried out by DAMAE Medical. DAMAE Medical is a French startup founded 10 years ago in 2014 by Anaïs Baru, David Siret, and myself. The company is based in Paris and has 30 employees. Since the company was founded in 2014, several LC-OCT prototypes have been built, becoming more and more efficient and more compact. 2 years after the company was founded, in 2016, we had our first clinical prototype. This prototype was installed at Saint-Étienne Hospital in France for the first clinical tests. Technical developments continue to be carried out in consultation with dermatologists from several European hospitals in France, Belgium, Italy, Spain, Germany. A total of 11 prototypes have been built, the last 3 being CE marked for research applications. And the last prototype included a video dermatoscope. And since the end of 2020, LC-OCT is commercially available. The device is called DeepLive. On this video, you will see the use of DeepLive by a dermatologist.
The portable probe has been designed to scan any skin site on the body. The integrated top-view camera allows instant positioning and precise navigation over the different areas of the lesion. DeepLive offers 3 LC-OCT acquisition modes: vertical imaging similar to histological sections, horizontal imaging down to 500 microns in depth, unprecedented 3D imaging performed within a few seconds, allowing a global understanding of the lesion. About 10 LC-OCT images are acquired every second, streaming in real time an unmatched level of vivo information.
Okay, now I will talk about the application of LC-OCT in dermatology. More than 100 independent clinical publications demonstrated the value of LC-OCT in dermatology have been published to date. And we have recently obtained the CE marking of DeepLive as a medical device for the diagnosis of skin cancers. Here are images of a basal cell carcinoma, a BCC. A nodule can be seen on both the vertical view and the horizontal view. And with the 3D image, it's possible to observe the carcinoma from different angles, to navigate through the skin, as you can see. LC-OCT is able to differentiate between the different types of BCCs. This is important because depending on the cancer type, the treatment is not the same, surgery or application of a cream. On the images, you can see obvious differences between a superficial BCC, a nodular BCC, and an infiltrative BCC. LC-OCT can be used for monitoring the treatment of superficial BCCs with a cream. In the case here, the lesion showed a complete response on both clinical and LC-OCT examinations. But in this other case here on your right, the lesion showed a complete response on clinical examination, but in reality, residual tumor was still present, and this was revealed by LC-OCT. Several studies have been conducted on the ability of LC-OCT to differentiate BCCs from imitators, such as sebaceous hyperplasia on your left and dermal nevus on your right. LC-OCT allows the evaluation of the margin in BCC surgery by imaging all around the lesion in real time. A recent multi-center study was carried out about the BCC diagnosis. It was on almost 2,000 cases, and the figures obtained are a sensitivity of 98% and a specificity of 93%. And the latest European medical guidelines for the diagnosis and treatment of BCC mention the good agreement between LC-OCT and histopathology and indicate LC-OCT as a useful technique. Okay, let's take a look at melanocytic lesions now. Here is an image of a benign nevus in good agreement with the histological image. And here is an image of an invasive melanoma. The image is very different, revealing nests of melanocytes similar to histology, to the histological image. And here are other images of melanoma. Thanks to the high resolution of LC-OCT, it's possible to visualize abnormal melanocytic cells and the abnormal proliferation of dendritic cells, which is characteristic of melanoma. DAMAE Medical has been working a lot on artificial intelligence to automatically analyze images. The company has developed an algorithm to detect and identify lesions in real time during LC-OCT imaging. And here, areas colored yellow indicate the presence of a carcinoma with a confidence level displayed above the image. Artificial intelligence helps the user to interpret images and make a diagnosis. And this facilitates adoption of the technique by the users. Okay, now I'm going to talk about LC-OCT combined with artificial intelligence for application in dermocosmetology. LC-OCT with artificial intelligence can be used for the quantification of skin at different levels. It can be used for the measurement of skin layer thickness and to study the morphology of the dermal-epidermal junction. It can be used at the cellular level for the quantification of keratinocytes, keratinocyte nuclei, and also for the quantification of melanin density and melanin distribution. LC-OCT can also be used at the tissular level for the study of the dermal fibers and blood vessels. Let's start with skin layers and dermal-epidermal junction. From 3D images, skin layers can be segmented to measure the thickness of the stratum corneum and the thickness of the epidermis. The ondulation of the dermal-epidermal junction can also be measured. To do this, an artificial intelligence algorithm was trained on over about 4,000 images acquired from more than 200 people with different phototypes from different ethnic backgrounds, male, female, of all ages, at different locations of the body. A study was carried out for quantitative comparison of healthy epidermis at different locations on the body. In this study, the metrics were epidermis thickness and ondulation of the junction. For example, depending on the location on the face, the ondulation of the junction changes, flat on the cheek, very ondulated on the forehead. Here, the thickness of the epidermis at different sites on the body was studied as a function of age on children. Children from birth to age 12. This was a study of changes in skin structure with age involving 100 adult women, aged between 20 and 70. An increase in stratum corneum thickness was observed on the temples and on the mandibles. A decrease in epidermis thickness was measured on the mandible, but no significant variation in the dermal-epidermal junction was observed. The effect of a skin product was evaluated. So here it was a moisturizing cream. So the effect of the moisturizing cream on the stratum corneum was studied. 60 minutes, 1 hour after application of the cream. An average increase in stratum corneum thickness was measured of 6%. And here it was, we studied the effect of a skincare product on skin. So here, 3 months after daily application of the product, a significant increase in the thickness of both the stratum corneum and the stratum spinosum was measured, plus 40% for the stratum corneum and plus 55% for the stratum spinosum. So this study clearly demonstrated an effect of the product. Here, it was a study of the effect of a product for the treatment of an inflammatory disease, psoriasis. After 8 weeks of treatment, a major change in skin structure was observed. In particular, the very undulated dermal-epidermal junction became much flatter. Now let's look at the quantification of keratinocytes. The nuclei of the keratinocytes in the epidermis can be segmented. The metrics obtained from the segmentation are keratinocyte density, nuclei volume, nuclei compactness, and number of cell layers. And finally, an atypia score can be given, taking all these parameters into account. For example, here you can see on your left a skin with normal keratinocytes, and on your right, a skin with abnormal keratinocyte with different levels of atypia. The segmentation of keratinocyte nuclei allows, for example, to study the maturation process of keratinocytes with age. A young skin on the left, 24 years old, and older skin on the right, 67 years old. So as you can see, in the older skin, the average volume of nuclei is higher, while cell density is lower. A study on 100 persons was carried out to quantify the keratinocyte maturation process across various body sites and various age. So I'm not going into detail, but a significant increase in keratinocyte atypia was observed with age here on the face. Let's talk about melanin now. The melanin can also be segmented. The algorithm was trained on the face for all phototypes, on healthy skin, and also on pigmented spots. So as expected, the amount of melanin increases from phototype 1 to phototype 6. And so here it was measured by on the cheek. The efficacy of a brightening product was evaluated. The same region on the cheek was imaged 56 days after daily application of the brightening product. The LC-OCT images reveal that the amount of melanin has decreased, and also that the distribution of melanin has become more superficial. So a certain efficacy of the brightening product was demonstrated in this study. The effect of a laser treatment of solar lentigo was studied. 5 days after laser exposure, the epidermis thickness increased due to inflammation. 28 days after laser exposure, the epidermis thickness became normal. And compared to skin before treatment, the dermal epidermal junction was less undulated, and the amount of melanin had decreased, which was the objective of the laser treatment. Dermal fibers now. The dermal fibers can be segmented. We can calculate the fiber density and an anisotropy factor. On your left, you can see the fibers of a young skin, 23 years old, and on your right, the fibers of an older skin, 55. So the difference is obvious. We are currently working on the segmentation of blood vessels in skin, but so this work is still in progress. I'm not going to talk about that, but this is still in progress. So I've given you briefly an overview of the possibilities offered by LC-OCT combined with artificial intelligence for dermocosmetic studies. For more information, I invite you to consult the publications on the subject. And you can also scan the QR code here to access publication and to access our booklet on dermocosmetic applications.
Yeah,
Camille,
yeah.
very briefly, I would like to talk about the combination of LC-OCT and Raman spectroscopy. Maybe it's of interest for you. So LC-OCT provides morphological information about skin. However, the interpretation of the images can be complex in pathologies with ambiguous morphological features or in early stage pathologies with small structural changes. So the interest of confocal microscopy is that this technique provides information on the molecular composition of a sample. So the idea is to perform local spectroscopic measurements at points of interest targeted by LC-OCT. So our approach is based on co-localization using two distinct devices. So it will be limited to ex vivo samples for the moment. So the calibration, the co-localization requires a correspondence between the spatial coordinates and the sample position under the two devices. So a calibration is first performed. The sample is placed in a sample holder, you can see here. And so the sample is placed under the LC-OCT device and a 3D image is acquired. The points of interest to be analyzed with Raman spectroscopy are targeted in the 3D image, and then the sample is displaced from the LC-OCT device to the Raman device, and the coordinates of the points of interest are calculated to acquire Raman spectra at this spectrum. So briefly, Raman spectroscopy here was applied to a tattoo. So a biopsy of a tattoo was analyzed, and the combination of LC-OCT and Raman spectroscopy provided complementary information on the tattoo, 3D location of the pigment, pigment type, and pigment density. The technique also provided information on the tattoo reaction. The presence of inflammatory cells, macrophages, was revealed by Raman spectroscopy, invisible with LC-OCT. So we have recently built a new system where the sample can be automatically moved between the LC-OCT device and the Raman probe, which will facilitate experiments. So to conclude this talk, LC-OCT is a recent imaging technique which combines the advantages of OCT and confocal microscopy in terms of resolution, penetration, and image orientation. Over 100 independent clinical publications have demonstrated the value of this technique in dermatology to date. LC-OCT can also be used in cosmetology for the quantification of skin at different levels. The use of artificial intelligence expands the application of the study, as we have seen. And finally, coupling LC-OCT to spectroscopic techniques such as Raman spectroscopy could enable morphological cellular level imaging along with local molecular analysis. So I would like to acknowledge and thank the many people who contributed to this work. The list is too long to mention all the names, and I thank you for your attention.